Good day. We are going to present group activity number 3, data mining. Get to, Getting to know the data part 2. Data visualization. The goal of data visualization is to communicate. Data must be represented graphically in order to be communicated clearly and effectively. Data visualization has been utilized extensively in a variety of applications, such as at workplace with reporting system, business processes, as well as task monitoring. More often, we can use visualization approaches to find data connections that might otherwise go undetected by only looking at the raw data. People nowadays has taken advantage of data visualization. Here are the basic concepts of data visualization. First, pixel-oriented visualization technique. The basic idea of this technique is to display as many data objects as appropriate on the screen at the same time by mapping each data value to a screen pixel and suitably arranging the pixels. This technique generates m windows on the screen, one for each dimension, for a data collection of m dimensions. A record's m dimension values are mapped to m pixels at the relevant points in the windows. The use of the pixels correlate to the values they represent. Here are some of pixel-oriented visualization techniques. Recursive pattern. When visualizing, it is possible to group data to make it easier to interpret. It works by combining various techniques, distinct pattern levels by defining the height and width of the different levels. A first level pattern could help to organize. The first allows you to analyze data over a year, while the second allows you to interpret data over a month. Circle segments. Divides a circle into k dimensions in according to the number of attributes k in the data collection. Each has its own property. Is then represented visually by coloring a single pixel. All qualities are close to the center, making it easier to contrast their ideals. Second, basic concept of data visualization. Geometric projection visualization technique. These techniques are an excellent alternative for detecting outliers and determining the relationships between features in multidimensional data. This technique does this by implementing information modifications and projections. When working with huge datasets, to minimize cluttered and confusing data created by the modeling approach, a clustering procedure is normally required to be used before the visualization technique due to an increase in availability of the information. Here are some of geometric projection techniques. First, scatter plots is a popular visualization approach that may be used in both 3D and 2D. The scatter plot graphs different properties of the data that are visualized on the XY axis in 2D and along the Z axis in 3D. Scatter plots can be used to identify correlations between attributes in any small dataset. If the dataset becomes too large or contains too many records, the scatter plot becomes complex and difficult to comprehend as more attributes are added. Radvis is yet another method for displaying multivariate data. It uses Hooke's law and a set of rules to map data to a 2D plane. Anchor points are typically indicated through characteristics. Third, parallel coordinates. If the data has several features, you may need several scatter plots to visualize all of them, which may be difficult to do. Look for patterns. Parallel coordinates are a popular approach for multivariate data. They function by visualizing each attribute on the vertical axis and lines linking each individual data point to the axis. The strength of parallel coordinates is the ability to discover relationships between a large number of properties. If you compare parallel coordinates to scatter plots, you'll notice that they have the same flaw. Because the dataset is too huge, it becomes easily crowded. Third, basic concept of data visualization. Hierarchical visualization technique. This technique depicts data by creating subspaces based on the properties of the data. Hierarchical approaches can be used. Sometimes certain data properties may be more important than others. Here is one technique, the tree maps. Rectangles are used to depict hierarchical data. A rectangle is assigned to each branch of the tree. Following that, each sub-branch gets allocated to a rectangle and so on until a leaf node is discovered. Depending on the option, the rectangle, the leaf node is colored, scaled, or both based on the attribute selected. This is an effective method for locating pertinent data. It is suitable for categorized data, yet when dealing with huge data sets, the outcome might be crowded. Yes.
Fourth,
Number 4.
graph-based visualization technique, where huge graphs are shown utilizing algorithm and abstraction layers to provide a clear perspective of the graph. For example, in a graph technique provided by Kilian Thiel, Fabian Dill, Tobias Cotter, and Michael R. Berthold, in the retrieved phrases as well as the times as represented by graph vertices. The phrases that appear during a specific time period are linked to the referring vertices. This type of visualization is less clear when searching through huge data sets, but it offers the advantage of speed. The ability to examine relationships and numerous volumes of data in a single graph is a benefit. Next. 5. Icon-based visualization technique. Data can be visualized by modifying the attributes of an icon or glyph based on the data. Chernoff faces was an early version in which data was mapped to various face parts such as the nose, lips, eyes, and so on. Consider how wealthy people behave are mappable to the Chernoff faced mouth. Rich individuals are symbolized by a joyful mouth, while poor people are portrayed by a sad mouth. Next. 6. Interaction visualization technique. Many visualization techniques are integrated with various interaction approaches to make greater use of them. One that was discussed previously mentioned in linkage, which allows selection and filtering on one visualization to impact another. First is the fisheye zooming. A detail on demand method can be utilized in a huge visualization to provide a better view of a special object component of the visualization. This technique is ideal for huge graph or pixel-oriented techniques. Second is the tooltips offering further information on a specified data or attributes could be used for detailed on demand. Next.
Data similarity and dissimilarity. Next. Data similarity and dissimilarity. Similarity measure. Similarity measure for two objects I and j will typically return the value 0 if the objects are unalike. The higher the similarity value, the greater the similarity between objects. Dissimilarity measure. A dissimilarity measure works the opposite way. It returns a value of 0 if the objects are the same. The higher the dissimilarity value, the more dissimilar the two objects are. Next. Data matrix versus dissimilarity matrix. Data matrix or object by attribute structure. This structure stores the n data objects in the form of a relational table or n by p matrix or n objects times p attributes. Each row corresponds to an object. As part of our notation, we may use f to index through the p attributes. Next. Dissimilarity matrix or object by object structure. This structure stores a collection of proximities that are available for all pairs of n objects. It is often represented by an n by n table, which is as follows, where Dij is the measure dissimilarity or difference between objects I and j. Next. Dissimilarity of numeric data. Distance measures are commonly used for computing the dissimilarity of objects described by numeric attributes. These measures include the Euclidean, Manhattan, and Minkowski distances. Euclidean distance, the most common distance measure. Let I and j be the two objects described by p numeric attributes. The Euclidean distance between objects I and j is defined as, and Manhattan distance or city block distance is the distance in blocks between any 2 points in a city. It is defined as the similarity of I and j is equal to summation of mod xi minus xj. Next. Minkowski distance, a generalization of Euclidean and Manhattan distances. It is defined as below, where h is a real number such that h is greater than or equal to 1. It represents the Manhattan distance when h is equal to 1 and Euclidean distance when h is equal to 2. Next. Both the Euclidean and Manhattan distance satisfy the following mathematical properties. First is non-negativity. A dissimilarity of ij is greater than or equal to 0, or distance ij is greater than or equal to 0. Distance is a non-negative number. Second, identity of indiscernibles. Distance I and I is equal to 0. The distance of an object to itself is 0. Symmetry. Distance of I and j and distance j and distance of I and j is equal to distance of j and I. Distance is a symmetric function. Triangle inequality. Distance of I and j is less than or equal to distance of I and k plus distance of k and j. Going directly from object I to object j in space is no more than making a detour over any other object k. Next. That's it. Thank you.